Okay. Hello, everybody. Good afternoon to all. This is again welcome second interactive session on this online course, Advances in Welding and Joining Technologies. I believe that up to this time you covered up most of the modules, and here I am trying to discuss very selective part, probably having some difficulties to understand this particular course. Of course, this if you follow the video recording of this course, most of the things is well explained in the most simplified language. And here, few topics and just to review it, maybe it will help you to understand the better way. And of course, at the same time, if you solve the assignment problem also of your own, so that will also be helpful to understand the subjects. And of course, this subject also having so many numerical problems also that this has been introduced just to understand, to cope up the very simple problems associated with the welding and joining technologies. So this is a very common questions, and for the live interaction session that maybe look into the Rosenthal's 3D equation. That is the most usually analytical solution we use in the welding problem, specifically to understand the temperature distribution. Again, I'll relook this to explain this Rosenthal's equation. And apart from these things, maybe you have some other queries related to the different process. But actually, I have not received any kind of the documented questions that already shared with this file. But here I didn't find any such questions raised by you itself. So I just prepared something based on my understanding, assuming that probably you might have some difficulties to understand this particular topic. Now, if you look into the analytical solution of the temperature distribution in a welding process, we need to solve the heat conduction equation. And if you follow this governing equation, it's a tangent heat conduction equation. So temperature can be represented as a function of time as well as the space also. Now, when we go for analytical solution of this particular problem, we need a lot of assumptions. Otherwise, we will not be able to solve this heat conduction equation for the welding problem. So, and the quality of the solution or variant of the solution actually depends on what assumptions you are considering to represent the welding process. Now, this governing equation is given, and in this case, we are assuming the infinite body such that we can neglect the boundary conditions, and assuming that along the X, Y, and Z direction, that body, the solution domain is infinitely long. So therefore, you don't have the scope to put very specific the boundary conditions with this assumption. So basically, we are trying to simplify the solution just to avoid the putting of the boundary condition, and for that purpose, we are assuming the infinitely long distance of this body. Another assumption is that instantaneous point heat source. So that means heat is released one particular point with the application of the laser or arc. That is another assumption, rather than any kind of the distributed heat source here. So this is assumptions, and initial temperature we are assuming, or reference temperature we are assuming as a 0. So that is quite with this assumption, this solution can be simplified and can be represented in this way. Temperature as a function of radial distance and time is basically Q by rho Cp 4 pi alpha T to the power 3 by 2 exponential minus R square by 4 alpha T. So here actually alpha is the thermal diffusivity. It's a ratio of thermal conductivity, and rho and C, that means multiplication of the density and the specific heat. And Q is the applied heat energy to the domain. And other properties, rho, Cp, rho, density, Cp, specific heat are defined. R is the radial distance. So R is can be represented square root of x square plus y square plus z square. And this is the solution. We are measuring with respect to the origin. So this is a particular point. We can estimate this is the temperature. And of course, this evolves with respect to time t. And if you see, this solution is actually with this particular assumption, the solution we are getting is the three-dimensional distribution. That means the spatial distribution as a function of x, y, and z. And this can be represented like that. The isothermal contour is basically a series of the sphere with the radius r. So that means this way equation represents isotherm means the constant temperature within the domain can be represented as a series of the spheres with respect to r. Now further, the different solution we can get also. In this case, we are assuming the infinite body, the effect of boundary condition can be neglected. And then we consider as an instantaneous line heat source. That means releasing the total energy, not a point, rather over a finite length of the line. And in this case, with these assumptions, we will be able to get the two-dimensional temperature distribution for this particular case. So here also we are assuming the initial temperature equal to 0. Now T as a function of R is the radial distance and time small t is the time here. You can get this kind of the solution, but here R is represented 2D as a function of X and Y radial distance. So here if you represent the isothermal contour is basically represent the series of the cylinders, and that actually vary with respect to time T. So if you see that when you're instead of the point heat source, when you're assuming the line heat source, then you're getting the solution of the temperature as a two-dimensional way. So here, specific these assumptions. Of course, there are lots of options are there because there's a different variants of the analytical solution of the different assumptions also. That is possible. Now, in a third step, if we are assuming the instantaneous plane heat source, then you will be able to get the one-dimensional temperature distribution. So here T as a function of X and small t time, we are getting this particular solution. And if we see the term Q by rho Cp 4 pi alpha T, here T is the time here. And if you see in this case 4 pi alpha T, the exponent of the 4 pi alpha T are different in this three different solution. So one is a 3 by 2, then 1, then half. Like that. And here we'll be able to get the isothermal contour is a series of the planes. So here we see three different variants of the temperature distribution you're getting, depending upon the what boundary what kind of the heat source you are representing. If it is a point heat source, three-dimensional temperature distribution. It is a line heat source, two-dimensional temperature distribution. And if it is a plane heat source, then you are getting the one-dimensional temperature distribution. And that this equation is quite simple to get this thing. So I mean to say that there is a different variant of the solution is possible, analytical solution in particular welding problem. Now question is that this point heat source, line heat source or plane heat source is basically can be related to different types of the welding processes. For example, laser welding system, it's more appropriate to consider the line heat source. And other cases you can define the even plane heat source also. In specific cases, other cases we can see, we can consider this as a plane heat source, and plane is the in this case a heat source acting over a plane. So that's why the different kind of the welding problem can be solved with this assumption. This is a very basic mathematical relation we are getting to understand the temperature distribution following the Rosenthal equation. Now we look into the analytical temperature distribution in a steady state situation. This is also Rosenthal solution, but in this case, we are getting the steady state means solution means this is a function of only space. There is no time component here. And of course, in this case, there is the assumption is that we are assuming the moving point heat source on a semi-infinite body. Semi-infinite body means that maybe one dimension is infinitely long and other dimension may be restricted, very finite. So that's why we can define as a semi-infinite body. And of course, Rosenthal equation, steady state flow, if we solution of the heat conduction equation and the steady state situation, we are getting with the semi-infinite body and point heat source, and there is no loss of the heat from the boundary. With these assumptions, we can find out the two-dimensional heat flow in a welding process for a very thin sheets of the infinite width. So along the width direction, it is infinitely long. So in that case, we are getting this solution T equal to T0 plus Q by twice pi Kh exponential Vx by twice alpha A0 VR by 2S. K0 is the basically modified Bessel's function of the second kind and the zero order. So you see that if you look into more realistic situation, then further the solution becomes more complicated. So here the Bessel's functions comes into the picture to get the solution of the heat conduction equation in the steady state situation. Now here we are talking about the semi-infinite body, what means one dimension is finite. Maybe in this case the thickness direction, we are assuming that finite thickness value, h is the workpiece thickness. That means other two dimensions are infinitely long, but thickness direction is a finite distance. Then with this situation, we are getting this two-dimensional heat flow equation. Of course, if we follow this equation, that it is actually this equation, one term is use the welding velocity. That is also included here. So that means temperature distribution can vary for the different welding velocity. So that is the one important solution to this situation we can utilize for to understand the temperature distribution in case of the welding process. Okay, so with this other, we are getting this solution. Now, here also we are using the moving point heat source. That means heat source is moving with particular velocity V and a semi-infinite body. And in this case, point heat source, no heat loss. Then again, we are getting the solution, three-dimensional solution of the equation is as a function of three-dimensional equation we are getting. So T equal to T0 Q by 2s pi K R exponential minus V R minus X base 2 alpha. In this case, you see that temperature 3D solution we are getting here. And R is a radial distance from the origin and heat source is moving along the x-axis with velocity V. And of course, in this case, the solution is maybe more simplified as compared to the previous one. Previous one, we were supposed to have modified Bessel's function was involved, and in that case, we were getting the two-dimensional temperature distribution for a finite thickness. Here we are getting the three-dimensional solution, and of course, with the also in case of the semi-infinite workpiece. But one of the difficulties of this kind of there is a singularity problem at the origin and of the coordinate system caused by the point heat source. Because we are assuming the point heat source, then we are not getting exactly the temperature distribution at this particular point. That means this is known as the singularity problem at the origin, and in the Cartesian coordinate system we are using to understand the temperature distribution of the moving heat source problem is specific to the welding process. So this is another type of the solution we are getting 3D. Now, this solution is more useful to understand very basic calculation, that cooling rate and temperature gradient from the Rosenthal equation we are getting. So equations we have derived. So equation we are getting the T equal to T0 plus Q by 2s pi K R exponential minus V into R minus X by 2 alpha. In this case, del X by del T at constant temperature, that is corresponds to the velocity V. And if you consider the along the x-axis, means along the x-axis we indicate the y equal to 0 and z equal to 0. And R, we can calculate R equal to square root of x square plus y square plus z square. From there we are getting R equal to x along the x-axis. So once you get it, put this value here in this equation, you are reaching T minus T0 equal to Q by 2s pi Kx, because R equal to x. So this is the temperature difference we are getting here. That T0 is the initial temperature or maybe reference temperature, we can say like that. Now you can further calculate from this equation T minus T0 equal to Q by 2s pi Kx. Here you can calculate the temperature gradient. Del T by del X at constant time equal to minus Q by 2s pi Kx square, which is equivalent to replace the X here because X is the variable here. X in terms of T minus T0 Q twice pi K. So put it and we'll be able to get minus twice pi K T minus T0 square by Q. So just replace the X here and we are calculating the temperature gradient. Now, as temperature, okay. Now we can calculate the cooling rate del T by del small t at a particular fixed space. The fixed X value we are getting the cooling rate can be del T by del small t, can be represented like the del T by del X by del T. And multiply, put this expression already calculated, V will be coming to the picture, reaching this particular expression minus twice pi kV T minus T0 square by Q. Now you can make some conclusion that cooling rate is also important in the welding process because that actually influences the microstructure during the welding process, or maybe we can to some extent predict the solidification behavior of the welding process. So that's why cooling rate is very important, as well as the temperature gradient is also important, because that both decides the solidified microstructure in the welding process. So now we can reach the particular conclusion from this expression that cooling rate is actually reduced significantly by preheating. By preheating means basically if you perform the welding process, preheat the sample at a certain temperature, that actually reduces the cooling rate during the welding process. How it can be, what we can explain this one, because you look into the expression, what is the expression about the temperature cooling rate? So T minus T0. So basically preheating basically increases the value of T0. So that's why total decreasing this value, and finally try to reduce the cooling rate by increasing the preheating. This is the one conclusion. Second, cooling rate decreases with increasing Q by V. So Q by V, Q is the heat input. Q is the heat input, and V is the velocity. So in that case, Q by V actually represents the heat input per unit length. So that is the combined effect of the what is the input when you are moving laser or arc at the very fast. So that means considering the effect of the velocity. So therefore that it represents the heat input per unit length Q by V. So when cooling rate actually decreases by increasing the Q by V. Q by V means increasing the Q by V. When heat input per unit length increases, in that case, cooling rate is actually decreasing. So this important conclusion we can find out, relate the cooling rate from this expression. And finally, temperature gradient actually decreases with increasing Q. That means with increasing the heat input, temperature gradient actually decreases. So from here, we can relate what way the cooling rate can be modified during the welding process, or which parameter has to be looked into to make a very high cooling rate or to make a slow cooling rate. And that kind of the relation will help to design the welding process, or maybe this temperature gradient and cooling rate is, again, I'm telling that actually influence the solidification mode and solidified structure. So that's why it's two are important to calculate. So this simple analytical solution, we can estimate this cooling rate and the temperature gradient of the welding process. Now, sometimes it's a confusion to understand the heat transfer in the overall heat transfer during the welding process. So we can calculate how to define the different terminology, the efficiency term during the welding process. One is the arc power. Arc power is basically the arc voltage into welding current that we can directly measure from the machines, welding machines itself, and even we can use directly you can measure the laser power also. So therefore, the total amount of the energy for heating the workpiece can be represented like that: Q equal to the efficiency term into Q0. Q0 is the arc power, that is the power supplied by the arc. But during this, when it is supplied the power to the substrate, to the workpiece, there might be some loss of the heat due to the radiation and convection. So therefore, not all the arc power can enter to the workpiece. Some loss will be, so that how we can count this loss? So that we can count eta is the weld thermal efficiency. So therefore, that weld thermal efficiency is Q by Q0. Now actually Q0 is the arc power, but Q actually goes to the amount of the energy that actually transferred to the workpiece. Now, when you transport the workpiece, the energy all may not be used to melt the material. So some part will be melting the material, remaining part might be lost by convection and radiation from the boundary of the domain of the workpiece. So that's why that amount we can see that can be defined as the melting efficiency. What is the actual amount is used for melting the material, and what is the supply to the workpiece. So therefore Q1 by Q is basically defined by the melting efficiency. Now here, when you calculate the Q1 is the total amount of the heat actually required to melt the well-full metal up to the melting point. That actually including the latent heat of fusion. Now, Q minus Q1, sometimes you can see consisting of the part that can be overheating might be there. That means superheating of the liquid might also be not just reaching the melting point. So might be overheated. So that part has to be counted in this particular case. Now, straightforward. we can count what is the actual amount of the energy utilized just to melt the workpiece. That can be counted also in different way. Q1 equal to V, the velocity, welding velocity, A, the cross section measured normal to the velocity vector, and rho is the density. This is basically indicates the mass flow rate, and then specific heat Tm minus T0. That means raising the temperature, the amount of the energy required, heat energy that raised from the room temperature to the melting point temperature. And of course, this is the L latent heat is used to melting point. What is the heat is required to change the phase from solid phase to liquid phase. So this we can simply calculate the Q1, and we can use these two different terminology, the weld thermal efficiency and the melting efficiency. We can simply calculate just to counting what is the amount of the energy supply and what is the utilized for the finally utilized for the melting of the component. Now here's some example also given that sometimes we find it difficult to understand the numerical problem also. So we just pick up one example. Bead plate welding of the very thick steel plate is basically carried out using the GTAW process at 200 ampere current and 10 volt. That can be measured, and 2 millimeter per second is the welding velocity. Based on the Rosenthal's 3D equation, calculate the 500 degree centigrade cooling rates along the x-axis of the workpiece for 0 and 25 degree preheating. Two different cases. One case is having 0 preheating, other cases 25 degree preheating. The arc efficiency is considered as 70% and the thermal conductivity is given. How to solve this problem? Now we have already seen that how to calculate the temperature gradient. Directly we can go to the temperature gradient along the x-axis. The del T by del X temperature gradient for a fixed time. Twice pi k T minus T0 squared by Q. That is one case. And here also we know velocity equal to del X by del T. Now cooling rate can be calculated del T by del small t equal to minus twice pi k V T minus T0 squared by Q. That we have already calculated. We have already explained. Now how to utilize the data from this example. So here it is, if you see when you calculate the cooling rate, two different temperatures are given, T and T0. T and T0 here we have written the calculate the 500 degree centigrade cooling rate. Here the 500 degree centigrade is basically equivalent to T, capital only T. And T0 is the preheating. One case is T0 equal to 0, other case is T0 equal to 25 degrees centigrade. And if we put this value, then we can calculate. Now, how to calculate the Q? What is the heat input? Q total. Heat input is basically power. We can calculate the applied current and voltage. So 200 ampere into 10 volt, but not all amount of the energy utilized for the melting. So some part, that's why arc efficiency is given 70%. So we multiply by the 0.7 also. 0.7 into 200 ampere into 10 volt, that actually increases the heat input. So that is equivalent to the capital Q. And then we put this value, put the other properties value is well defined, velocity is also defined, and we can calculate that without preheating, before welding, that we are getting the cooling rate around 71 degrees centigrade per second. But when there is a 250 degrees centigrade, here the 250 degree preheating. So if we consider the 250 degree preheating, then we are getting that only 20 degrees centigrade per second. That means if there's a preheating, then cooling rate is actually low. So this is this strategy or this analogy is actually helpful to design the different kind of this welding process, how to reduce the residual stress. This concept can be utilized in that way. Now, there are also sometimes we understand that phase transformation in basically equilibrium and in a welding process, how to utilize the phase diagram to understand the different microstructural phenomena associated with the welding process. Usually we use the three different phase diagram. One is the equilibrium phase diagram, time temperature transformation diagram, TTT diagram, and continuous cooling transformation diagram. These are the three important phase diagram. We can use it for the different purpose. So equilibrium phase diagram is basically represent for the binary alloy, we can get all information about the different phases. And this perform under equilibrium condition means that cooling is very slow actually. So mathematically the infinitely slow cooling rate we are following. Based on that, the equilibrium phase diagram has been developed, constructed. So here we'll get the only information about at what composition, what kind of the phases exist in a binary phase alloy system. So that information is there in the equilibrium phase diagram. And if you remember that here x-axis represents the composition and y-axis represents the temperature. So at particular temperature and particular composition, what are the phase exist for a binary alloy system, that information will be able to get them from the equilibrium phase diagram. Now here time temperature transformation diagram. This is also so that what transformation happens, how much time is required for an isothermal transformation. That means at constant temperature, how much time is required for the transformation for one phase to another phase. Okay, but practically it's not very important, because practically transformation may not happen at constant temperature. So temperature can also vary. So that's why, but at least we know that what kind of the at temperature, what kind of the transformation, what phases transformation easily happens. That information will be get from the time temperature transformation diagram. But most practical usable diagram is the CCT diagram, because here we represent the continuous cooling transformation diagram, and we will get that constant cooling rate that can make a distinguish what kind of the phases can follow if we follow the different kind of the cooling rate. So that's why continuous cooling transformation diagram is mostly used to understand, to design the heat treatment process for the different kind of the alloy system. And we know that after welding process, we usually perform the heat treatment process to improve the different mechanical properties or to reduce the residual stress. That is usually performed for the heat treatment. So then heat treatment, what are the in heat treatment process, at which temperature to raise the temperature, what cooling rate can we follow. All this information can be, we can get all this information from the CCT diagram. So that's why it is very important for practical use of the design the path of the heat treatment. The CCT diagram we usually use it. Now, but in practice, the weld zone is actually subjected to a variable cooling rate, not one different zone. That cooling rate can vary also. So that is the one important thing. So variable cooling rate. So the different structure, different phases, mixture might form. And melt zone is basically associated with the molten zone is the solidification, but heat effective zone is mainly associated to the solid state phase transformation. That information will be able to get it. So here you can get some iron carbon diagram to understand the phase diagram. That equilibrium phase diagram will get the different phases at the different temperature, and x-axis represents the weight percentage of the carbon, and that is increasing order towards the right. And you see there are 4 different single phases exist. Austenitic phase, ferrite, alpha ferrite, delta ferrite. Delta ferrite is basically high temperature phase, and alpha ferrite is the low temperature phase. And beta is the basically cementite phase. So these are the different phases information we'll be able to get from the iron carbon equilibrium diagram, and what composition they exist, that we can see. And if you see from the diagram, phases also there, and in certain parts, certain temperature range, composition range, will get the mixture of the 2 different phases. So that's why it's a very important the phase diagram to understand what are the different phases, what temperature, and what are the expected microstructure. You'll be able to get it. That information we can explain, just look into the phase diagram. Now, try to look to some extent the solidification in welding and casting process. So how solidification occurs? So here, the solidification from liquid phase happens. Nucleation is basically getting the favorable conditions, the minimum amount of the energy to start the nucleation process, energy barrier repeat is getting, then start formation of the solid particle at the particular position, and it will try to grow. And when it is completely grow, complete liquid phase is converted to the solid phase, then you can say the complete phase transfer, the solidification is completed. The like way we can explain the solidification behavior. But in this case, the driving force for the homogeneous nucleation is basically undercooling is the main driving force. And in this case, the phase transformation happens to different phases, steps. One is the first nucleation happens, then it follows the growth stage. And nucleation involves the very small stable particles of the new phase, and that exist from the liquid phase, and finally try to grow in the completely disappear of the liquid phase and completely converted to the solid phase. So this way we can understand the solidification process. Now, in solidification, The progress of the phase transformation is basically nucleation and growth, but nucleation might happen homogeneous nucleation process and heterogeneous nucleation process. Homogeneous nucleation is basically formation of the critically sized solid from the liquid, and of course in this case undercooling is the main driving force to start the homogeneous nucleation process. And whereas heterogeneous nucleation process, we need some kind of the external interface to start the nucleation process. So therefore, the energy barrier or energy required to start the homogeneous nucleation is much more as compared to the heterogeneous nucleation process, because heterogeneous nucleation start from the pre-existing surfaces or any interfaces. The heterogeneous nucleation starts. So that's why, in this case, the required energy to start the nucleation process is relatively less in this case. So that's why we can homogeneous and heterogeneous nucleation process. I think in this way, I stop here. So thank you very much for your time attention. Now we'll try to look into any kind of the discussion. If there is any questions, query in the live interaction. Okay, so I can see from the question raised that explain the short CMT. Short CMT means I understand the cold metal transfer I'm talking about. What I understand, and this cold metal transfer is the kind of advanced version of the gas metal arc welding system. I can say the more controlled way metal can be transferred in the CMT process. But if you try to understand the gas metal arc welding process, there you can see that in gas metal arc welding process, I think there, if you see that when metal transfer happens, is actually integral part of the system. But you don't mechanically control the transfer of the droplet transfer, droplet detachment, that kind of the phases, we don't follow it. But in CMT, actually, the metal transfer happened in the short circuit mode. Short circuit mode means that when there is a gap is there between the arc is created, arc meld the material, the wire, then create the droplet, and droplet touch with the workpiece. When it is touched with the workpiece, then it creates the short circuit. When short circuit is there, they suddenly raise the temperature, decreasing the surface tension force, and detach the droplet to the substrate. But when detaching the droplet and transfer to the substrate, here we can use some mechanical system just to detach the droplet from the wire. So when using the mechanical system, and this droplet detachment actually happens with a very high frequency. USP means ultra short pulse laser welding system. What I understand this thing. So ultra short pulse laser system is different from the conventional laser system because the pulse duration in this case into 10 to the minus 15 second, the femtosecond. Femtosecond, picosecond to femtosecond level, 10 to the minus 12 to 10 to the minus 15. In that range, the duration of the pulse exists in case of the ultra short pulse laser system. But conventional laser system, the pulse duration can be millisecond, microsecond, nanosecond even. So that comes under the conventional laser weld system. But when it is the 10 to the minus 12 to 10 to the minus 15 second pulse duration, in that case is the ultra short pulse laser system. Actually, ultra short pulse laser system is the mainly utilized for the machining process. So just to very quickly, very precisely remove the material, ultra short pulse system can be utilized. But this can be used in the very specific way in case of the welding process, and very specifically when the frequency is very, very high. In that case, we can use the ultra short pulse in the laser system in case of the welding process. And mostly this ultra short pulse laser welding system we can use in particular polymer that through which the transfer and the laser light is transferred to that polymer. And suppose here you use joining the two different polymer, but this ultra-short pulse, we use the wavelength of the laser in such a specifically ultra-short laser that it is transparent to the, it passes through this particular polymer. And at the interface, the heat will be released and the two components can be joined together. Okay. And that is the beauty of the ultra-short pulse laser system. But the same polymer cannot be used in the simply millisecond or microsecond laser, because the laser light will basically transparent to the this thing. It will simply pass without hitting the substrate. So that's the way we can use the ultra-short pulse laser system. This thing in this case, and this can be used very precise, very small location if you want to join. And in that case, we can use the ultra-short pulse laser welding system. I think I have answered your questions. These 2 questions raised. Any other questions? You can type your questions here if you. Yes, ultra-short pulse laser is basically Mr. Anil Kumar. Okay, so ultra-short pulse can be used for the laser transmission welding. Laser transmission means the laser light is transparent to this particular material. So in that case, plastic can be joined. So in that case, when the ultra-short pulse laser and transparent to this, because ultra-short pulse is the this very short pulse duration, so that is transparent to the particular polymer plastic. But when if you want to join two polymer, although it is transparent to this particular laser light, so at the interface, they will be releasing the laser energy, and the interface that can be joined together, because this is the interface. So definitely interface, or laser light will be release the heat energy there, and then if you press it, then these two components can be joined. This is called the laser transmission welding. And in laser transmission welding, ultra-short pulse laser can be used to perform the laser transmission welding. Ultra-short pulse means simply understand that pulse duration is very, very short. So mechanism of the heat generation is something different from the conventional laser. So in this case, the laser material interaction are different in case of the ultra-short pulse system as compared to the conventional laser system. Conventional means basically the millisecond, microsecond laser system. Anything else? Any other questions you can raise? Okay, I think there is no other questions. Maybe I can stop here. Thank you. Thank you very much. Okay, so I stop here. Maybe please close it. Yeah. Okay. Oh, thank you.